This is my lab video for motion of a falling object. In this lab, the purpose was to measure the motion of an object after dropping it from a set height at rest and compare its motion to two computer models, one that accounted for only gravity and one that accounted for both gravity and drag. And as a quick overlook, the main result of this lab was that the computer model that used gravity and drag was a lot closer to the observed results than the one with just gravity. The fundamentals of this lab include Newton's second law of motion, which is given by the net force equals mass times acceleration. In this case, the net force is equal to the force of gravity plus the drag force. We also use Newton's second law of motion to get the velocity update formula and the position update formula to keep track of where the ball is and how fast it's moving in space. The force of gravity is given by the gravitational force equation, as seen here, and on Earth it works out to be negative mg/j hat. The drag force in this case was equal to the negative of some proportional constant times the square of the speed times the direction of the drag. In this experiment, the model consisted of the system being the paper ball and the surroundings, which were the earth and the air. The initial conditions was that the position was at 0, negative 0.0012430, and the initial velocity was also just 0. The total time that the ball fell was 0.533 seconds, and time was measured every 0.033 seconds since the frame rate was 30 frames per second. Here's a screenshot of tracker, and the axis started at the 0 position right about where the ball was first dropped, and the ball fell in the negative y direction, as seen in this video. You can see that the velocity was slowly starting to increase as it fell for a longer time. For the code of the gravity-only model, we had the proportionality constant set to 0, that way that the drag force equals 0 and the net force was based only off of the weight force or the gravitational force of the ball. We also had the ball estimated to be 0.0045 kilograms, since that's the average weight of a piece of paper, and we input the initial conditions and the delta t, which was stated to be 0.033 seconds. Then we used the velocity update and position update formula to keep track of where the ball was and showed arrows of the forces acting on the ball at each time point. For the model that had gravity and drag, the code was pretty much the same all around, except for the proportionality constant for drag was not 0. It was 0.00239, and this was found through trial and error to figure out at what value the final position equaled the final position in the actual experiment. These were the graphs of the results from the lab. As you can see, the model that had just gravity started to deviate from the actual position in the experiment the further along we got. In the middle, you can see that none of the models really lined up too well, but towards the end, the model with drag ended at the same spot that the experiment was. The error in this lab could have been that the positioning tracker was not accurately measured, since the ball was blurry at different time points. Additionally, the ball was spinning as it fell, which could have affected how the drag was slowing down the acceleration and could have caused the proportionality constant in that to not be a constant number, which we did not account for. Additionally, the ball may have not been crumpled well enough, which would have caused further air resistance that would have slowed down the ball than was accounted for. So, on to our discussion question. First, what does it mean? And our question was, which models predict a terminal velocity? And in this case, the model that included drag does predict the terminal velocity. The gravity-only model shows that the acceleration was constant and the velocity was increasing at the same rate. However, when drag was included, the acceleration was not constant and it started to decrease as the velocity got quicker, leading to a terminal velocity where given enough time, the velocity would level out and not be able to go any higher. And for the what if question, imagine that the object was initially thrown downwards and had some initial velocity in the negative y direction. Would the terminal velocity be the same or different? And in this case, the terminal velocity would be the same because the drag force, which cause the terminal velocity is based on the magnitude of the velocity, not what the initial velocity is. It would have reached the terminal velocity quicker, but it would have been the same terminal velocity. This is seen by the code being edited to have an initial velocity of -1 in the y direction, and it leveled up at about the same number. It just got there quicker. And that is all I had for this lab. In this lab, we talked about Newton's second law of motion and how it applied to non-constant forces, and including the force of gravity and drag acting in opposite directions, causing the acceleration to change. Thank you.